10.6. Diffraction. The shadow cast by an opaque object close to the region of geometrical shadow. There are alternate dark and bright regions, just like interference. This happens due to the phenomena of diffraction. 10.6.1. The single slit. In the discussion of Young's experiment, we stated that a single narrow slit acts as a new source from which light spreads out. Even before Young, early experimenters, including Newton, had noticed that light spreads out from narrow holes and slits. It seems to turn around corners and enter regions where we would expect a shadow. These effects, known as diffraction, can only be properly understood using wave ideas. After all, you are hardly surprised to hear sound waves from someone talking around a corner. When the double slit in Young's experiment is replaced by a single narrow slit illuminated by a monochromatic source, a board pattern with a central bright region is seen. On both sides, there are alternate dark and bright regions, the intensity becoming weaker away from the center. Refer adjacent figure. To understand this, go to adjacent figure, which shows a parallel beam of light falling normally on a single slit Ln of width A. The diffracted light goes on to meet a screen. The midpoint of the slit is M. A straight line through M perpendicular to the slit plane meets the screen at C. We want the intensity at any point P on the screen. As before, straight lines joining P to the different points L, M, N, etc. can be treated as parallel, making an angle theta with the normal MC. The basic idea is to divide the slit into much smaller parts and add their contributions at P with the proper phase differences. We are treating different parts of the wavefront at the slit as secondary sources. Because the incoming wavefront is parallel to the plane of the slit, these sources are in phase. The path difference NP minus LP between the two edges of the slit can be calculated exactly as for Young's experiment. From adjacent figure, NP minus LP is equal to NQ is equal to A sin theta is equal to A theta. Equation 10.21. Similarly, if 2 points M1 and M2 in the slit plane are separated by Y, the path difference M2P minus M1P is equal to Y theta. We now have to sum equal coherent contributions from a large number of sources, each with a different phase. This calculation was made by Fresnel using integral calculus, so we omit it here. The main features of the diffraction pattern can be understood by simple arguments. At the central point C on the screen, the angle theta is 0. All path differences are 0 and hence all the parts of the slit contribute in phase. This gives maximum intensity at C. Experimental observation shown in adjacent figure indicates that the intensity has a central maximum at theta is equal to 0 and other secondary maxima at theta equivalent to n plus 1 by 2 lambda by A and minima 0 intensity at theta equivalent to n lambda by A, where n is equal to 1, plus minus 2, plus minus 3 and so on. It is easy to see why it has minima at these values of angle. Consider first the angle theta where the path difference A lambda is lambda. Then theta is equal to lambda by A. Equation 10.22. Now divide the slit into two equal halves, LM and MN, each of size A by 2. For every point M1 in LM, there is a point M2 in MN such that M1, M2 is equal to A by 2. The path difference between M1 and M2 at P is equal to M2P minus M1P is equal to theta A by 2 is equal to lambda by 2 for the angle chosen. This means that the contributions from M1 and M2 are 180 degrees out of phase and cancel in the direction theta is equal to lambda by A. Contributions from the two halves of the slit LM and MN therefore cancel each other. Equation 10.22 gives the angle at which the intensity falls to 0. One can similarly show that the intensity is 0 for theta is equal to n lambda by A, with n being any integer except 0. Notice that the angular size of the central maximum increases when the slit width A decreases. It is also easy to see why there are maximum at theta is equal to n plus 1 by 2 into lambda by A, and why they go on becoming weaker and weaker with increasing n. Consider an angle theta is equal to 3 lambda by 2A, which is midway between two of the dark fringes. Divide the slit into 3 equal parts. If we take the first 2/3 of the slit, the path difference between the two ends would be 2 by 3A into theta is equal to 2A by 3 into 3 lambda by 2A is equal to lambda. This is equation 10.23. The first 2/3 of the slit can therefore be divided into two halves which have A lambda by 2 path difference. The contributions of these two halves cancel in the same manner as described earlier. Only the remaining 1/3 of the slit contributes to the intensity at a point between the two minima. Clearly, this will be much weaker than the central maximum, where the entire slit contributes in phase. One can similarly show that there are maximum at n plus 1 by 2 into theta by A, with n is equal to 2, 3, so on. These become weaker with increasing n since only 1/5, 1/7, etc. of the slit contributes in these cases. The photograph and intensity pattern corresponding to it is shown in adjacent figure. There has been prolonged discussion about difference between interference and diffraction among scientists since the discovery of this phenomena. In this context, it is increasing to know that Richard Feynman had said in his famous Feynman lectures on physics, "No one has ever been able to define the difference between interference and diffraction satisfactorily. It is just a question of usage, and there is no specific important physical difference between them. The best we can do it, roughly speaking, is to say that when there are only a few sources, say 2 interfering sources, then the result is usually called interference. But if there is a large number of them, it seems that the word diffraction is more often used." In the double slit experiment, we must note that the pattern on the screen is actually a superposition of single slit diffraction from each slit or hole and the double slit interference pattern. This is shown in adjacent figure. It shows a broader diffraction peak in which there appear several fringes of smaller width due to a double slit interference. The number of interference fringes occurring in the broad diffraction peak depends on the ratio D by A, that is, the ratio of the distance between the two slits to the width of a slit. In the limit of A becoming very small, the diffraction pattern will become very flat, and we will observe the two-slit interference pattern. Refer adjacent figure.